in this class. So the last time you had a lecture from me was 2 weeks ago. So where were we and where are we? Things we've talked about in mechanics are things having to do with mechanical properties of materials. And we did two simple special cases that we've covered somewhat. One is fluid mechanics, which we covered the special case of hydrostatics in some detail. And the other is elasticity, which we did not in maybe as much detail, but we did the special cases of stretching and bending. And then you had one lecture on more general constitutive laws, meaning material properties, from Professor Kirby while I was gone. Now we're starting in this section, which is more like the machines, solid, rigid body mechanics part of things, and we started talking about power and energy. And that's where I'm going to continue today. And some of this is background for the lab, which starts today, and some of it is general background for the project, which you have coming up. And some of it is just good for you to know as an introduction to mechanical engineering. Okay, so how does it go? So we have two confusingly related facts, and they're confusing because they're not completely independent, but they're not exactly the same thing, and it's very easy to get mixed up about these things, and it's even easy to get the right answers to questions from wrong reasoning. So one thing is we have, for any closed system, and by closed we mean, just to think of it as a cartoon, is a fixed set of atoms. Not that we're talking about atoms, but what I mean is it's a fixed collection of material. There's not material coming into the system or coming out of the system. This is the kind of thing you deal with in thermodynamics. And most basic laws are most clearly expressed when you express them with respect to closed systems. So if you're ever confused about something, you have to be able to go back and think about how the basic equations are used are reflected in a closed system. So for a closed system, we have this important thing, which I'm going to call one, is linear momentum balance. And it says that if you look at the system, no matter how complicated it is, in fact, it doesn't even have to be parts which are touching each other. The system could be any collection of material you want to pay attention to. If you look at the external forces acting on this system, and they show in a free body diagram, and this thing is called a free body diagram because the word body in this context means system, and the system could have various parts. It's still called a, quote, body, even if it's many objects. In this free body diagram, you show the external forces, and it's very easy to make the mistake to try to include internal forces, but they don't show in this model of a closed system. You look in a closed system at what the influence of the outside world is on the system, and if you take all these external forces and you add them up, so this is a sum over all external forces, and this system, however complicated it is, still satisfies this equation. And this is this COM stands for center of mass. And this is if you like, a theorem in mechanics, it's a postulate in mechanics, it's a fact of mechanics. It depends on which things you think of as assumed and which is derived, and whether you think of mechanics as a mathematical subject or physical subject. But this is something nobody's going to argue about with you unless they're interested in things that are traveling near to the speed of light or things which are much smaller than atoms. Now, there are other ways of expressing this thing. M is the total mass. So this is the total mass of the system. And that means somewhere in this system there's a place which we'll call the center of mass. It's called the center of mass, and sometimes people use the letter G for it. I don't know why. And sometimes it's drawn with this little symbol here. It looks like a nautical symbol representing this location. And this location is not necessarily fixed in the object. For example, if you're drawing a free body diagram of me, the center of mass is somewhere at the intersection of these two lines now. But when I'm in this position, the center of mass is over here. And when I'm doing crazy things and dancing around and the wind is blowing on me, the center of mass, if you made a movie of it with me, it would be a little dot which is moving around funny ways with respect to my body. But that dot would be moving, obeying this equation with the total forces on me. Now, if the object is simple, like it's a rigid object, a so-called rigid body, then the center of mass is fixed in the object, and you can paint it on the object. So if I suddenly died and had rigor mortis, you could paint the center of mass in the middle of my belly here, and then when I moved around in my rigor mortis with forces on me, then you would see F equals ma being applied to that particular dot there. But it's a confusing little fact. For example, let me just give you one that I use in my dynamics class. If I have some object like this, and all I apply is a force here on this. So this is, if you like, a square block on a frictionless plane, or it's a cube out in space, and I apply a force to this corner, and as this moves, I always keep this force constant, always pointing in this direction. So however it moves, I apply force to this corner, and I'm always pulling it in that direction. For example, I put a little peg here, and I tie a thread, and I hold the thread a few hundred yards away, always tugging on it. So the direction of the thread is always this direction, however this tumbles around. How does this point move when I apply this force here? This point moves here according to the equation F equals ma. And that means it moves in a straight line which is parallel to this one, and it moves along like this. So this would be the motion of the center of mass. Okay, that's what linear momentum balance says. It says, however complicated the system is, the center of mass of the system obeys the famous equation F is equal to ma, and it's a vector equation. Now we have the other big law. There's going to be three big laws in this class. So we have one is linear momentum balance. The second one, and I'm going to do this a little out of order to keep it consistent with what I did before, is the first law of thermodynamics. Thermodynamics, which is sometimes called the conservation of energy. And what does it say is that you can think of energy as like a fluid-like thing. It's hard to imagine anything but this being true. We're so used to it, it's hard to imagine this statement has content. But it says that for a closed system, the energy flow into the system is equal to the rate of change of the energy of the system. And it almost seems like, what do they call it, a tautology, a definition, but it's not really that. And I tried to convince you that it's not that, like the same with money. The flow of money into the United States is not the rate of change of money in the United States, because money can be created or destroyed. And energy isn't like that. It can't be created or destroyed. How can energy flow into the system? Well, sometimes in thermodynamics they call this W dot, the work rate. And sometimes they would call this E dot, meaning the rate of change of the total energy. That W dot is misleading, but it still gives you a sense that there's a rate of something going on here. And what are the kinds of things that can contribute to this W dot? One is that you can have forces dotted with velocities. And this could be various forces dotted with various velocities. And another is you can have a heat flow into the system. And another is you could have electrical energy into the system. So some voltage times a current. And then what's the energy the system can have? Well, it has this 1/2 the mass total times the velocity squared of the center of mass. That's the kinetic energy of the system as a whole. It's not really the kinetic energy of the system, though. So if you think of your system again as my body here, and now my body is floating in space, and you apply forces to my body, and let's say you apply two forces to my body. You apply one to my head, and you apply one to my foot, and they're in opposite directions. And if they're in opposite directions, and they're equal forces in magnitude, then the acceleration of my center of mass will be 0. So there'll be no change in the velocity of my center of mass, and this term won't change at all. Yet, the force on my head does work, because there's a force times velocity at my head, and the force at my foot does work, because there's a force times velocity at my foot. And so there's work being done on the system, and not only that, it moves. My body starts spinning or tumbling or distorting. So this is really not all of the kinetic energy of the system. There's what I could call an internal kinetic energy. And if it's a rigid object, that internal kinetic energy is just a rotational energy. But if it's an object that's got many parts, this just has to do with other motions associated with motion relative to the center of mass rather than motion of the center of mass. And then we have also sort of chemical potential energy. We have springs. We could have batteries. So all different kinds of internal energy in the system. Okay, now what's confusing in simple mechanics problems about the connection between this first one and the second one is the first one, if we do a little math, and I showed you how to do that math in one dimension, but the first one says that if we look at the total force on the system, and by the total force we mean the sum of all the forces, and we take the dot product of that with the velocity of the center of mass, that this is equal to d by dt of 1/2 of the total mass of the system times the velocity of the center of mass squared. So back over here, we have however complicated the system is, and however complicated the forces are on the system, the whole system obeys the equation F equals ma. If what we mean by the force is the total force in the system, what we mean by mass is the total mass of the system, what we mean by acceleration is the total acceleration of the system. We take this equation as a vector equation, take the dot product of both sides with the velocity, recognize that acceleration dot velocity is the derivative of 1/2 v squared, and then we get this result over here. Now this looks like some kind of power, and this looks like some kind of change of energy, but actually this term doesn't show up anywhere on the left-hand side of this equation. Why doesn't it? Is because these forces are multiplied by the velocities of the point where the force is applied. So these are adding up these forces, and this is the velocity of the point of application. So let's just go back to me floating in space with two forces on me, one in this direction, one on my feet. Let me just finish this and I'll take your question. One force on me this way, one on my feet. If I look at this term here, it adds to 0. If I look at this thing here, it adds to 0. With a force here on me here and an equal one on my feet, then the mass times acceleration, total mass times acceleration center mass is 0. So with those forces applied to me, this term would be 0. Yet, with those forces applied to me, there would be work. Those forces would do work. They would have power acting on me, because pushing on my head will move it sideways, and there will be work on my head this way. There will be work on my feet. There will be change in the energy of the system. So the system will change energy. Where will it show up? In this equation, the first law of thermodynamics, it will show up over here. So this looks like the first law of thermodynamics, but it's not. Unfortunately, you can pretend, you can do equations with making the mistake of thinking of this as the first law of thermodynamics. So let me just show an example. So as an example, let's do a bicycle rider accelerating. Okay, so how does this look? You have a person on a bicycle. The bicycle has a triangular rear frame. The front frame is usually not quite triangular. It's got an extra little piece there, comes down like this. In the old days, we used to have handlebars that curved around like that. There's a seat like that. Person's out there like that with their legs like that. And they've got... Okay, so there's the bicycle rider on the ground. And let's, just to make it simple, let's neglect air friction. And you know, the way we say it in the homework problems, we say there is no air friction, which is a lie. Of course there is air friction. What we mean is you like to do the problem with the approximation that the air friction is negligible, which for bicycle riders, for most of what they do, is a good approximation if they're going, say, less than 10 miles an hour, and is a horrible approximation if they're going anything like 20 miles an hour. Okay, so here's this bicycle rider, and it's easy to talk about acceleration and so on, but it's easy to get confused. So let me try to both confuse you and unconfuse you at the same time. Okay, now what was your question?
Energy flow, so it's one over VI.
Say again?
What's VI, the energy flow, like, you know,
This one here?
yeah, what's VI?
This one? VI? Oh. Same symbols, VI, right? No equation is good unless you use the same symbol to have two different meanings in the same equation. Otherwise, it wouldn't be confusing enough. Okay, so this was voltage times current. And I mean by this the electrical power into the system. Okay? Yes?
You said like how if force was applied on opposite sides to you, like it will become zero? Because
If forces are applied to opposite sides,
like the net force.
I become zero.
No, that's not what I said.
Okay, say again.
You said like one is applied to at your head and one is the other is applied at your feet.
The sum of the forces is zero.
Right. But
Yet, my energy will change.
because the acceleration is not zero.
The acceleration of the center of mass is zero. So if I apply one to my foot that way, one to my head that way, 100 newtons that way, 100 newtons that way, the sum of the forces is zero. So if you look at the center of mass, it will not accelerate.
Yeah.
And even if I tumble around and use my muscles, those are all internal forces. They have nothing to do with the linear momentum balance equation. My center of mass will not
So
accelerate.
this is like a kind of a circular motion.
It could be circular motion or it could be crazy tumbling. But how does it show up in these equations? In this equation, we'll have to get 0 equals 0 because the sum of the forces is 0. In this equation, something's obviously going on. Forces are applied, motion is occurring, there's some kind of energy flow. And this term is not 0 because here we have this force times this velocity, which is not 0. This force times this velocity, which is not 0. So these add up. They don't cancel. The force and velocity are in the same direction. They add up. The force and velocity in the same direction. They add up. So this is not 0. This one has to be 0 because F equals ma says so. On the other hand, somehow that power has to show up as a change of energy here. How does it show up? It could show up two different ways. It could show up as a change in the internal kinetic energy, and it could also show up as a heat term. So I should put heat here also. Could also make me hotter. And you, yes?
Why does that term have to go to 0 be based on force times ma?
Why does this one have to go to 0 based on force times ma? Because we have this theorem. The sum of forces is the mass times the acceleration. For any system, no matter how you're applying forces to it, no matter how it's moving or distorting. You can call this a theorem, you can call it a postulate, you can call it an axiom, you can call it a fact. Nobody argues with it. But as I said, it's subtle because it makes predictions which maybe are somewhat unintuitive to you. That this thing, as you apply this force here, it wiggles like oscillates, but the center of mass goes as if the force was applied to the center of mass. Yes? No?
What's Q?
What's Q is this thermodynamics. They use this letter Q for the flow of thermal energy into the system. Yes? I'm in my language here right now, I'm calling that internal kinetic energy, yes.
Okay, so rotational is
I don't want you to memorize those words because different people use the words different ways, but right now that's the way I'm saying it, right? I'm saying there's a kinetic energy associated with the center of mass, and there's a kinetic energy associated with motion relative to the center of mass. It happens that kinetic energy, another theorem, can be factored into the sum of these two terms. That's a whole bit of algebra to work that out, but it happens it factors that way. And this is the kinetic energy associated with motion relative to the center of mass, which I'm calling now internal kinetic energy. But that's it's a black hole of a verbal argument we can make about that language. And actually, because this connection is so subtle, lots of people make mistakes about these words and what's inside and what's outside, and there's really big confusion about this in people who should know better, like people who are professors of biomechanics and so on. So, simple answer to your question, I'm calling rotational kinetic energy internal kinetic energy right here, right this second. I don't promise to stick to that vocabulary. Okay. Okay, now let's go back to this bicycle. So if we draw a free body diagram of the bicycle, we have the bicycle here, and I'll just draw it as a blob like this. I don't need to get into the details. What forces do I have? Well, here's the center of mass of the bicycle and the rider. So I have the total mass times g on this. Actually, there's forces all over the bike, but they're equivalent to a single force at the center of mass of the whole bike. There's some force here, there's some force here. If this front wheel is very light, and there's not much friction on the bearings, I can neglect the sideways force at the front wheel, or I could just put a teeny little force here, or I could say it's approximately 0. And then this force back here is all important, this force. Now, for this bicycle, what is the power of the external forces on the bicycle? And I did this 2 weeks ago in this room, so most of you should know the answer. Take out your clicker. I'm not ready for the vote yet. I don't have this transmitted, but if you do anything interesting, I'll tell you about it. Okay. So looking at this system, we can look at two different things. We can look at linear momentum balance for this system. For that purpose, we might keep track of the x direction of the motion. And we can also look at the first law of thermodynamics for this system. And we can see what these two things tell us. Okay. What does linear momentum balance tell us? It tells us that this applied F, this force here of the rear wheel, ground on the rear wheel, equals the mass times the acceleration. And what do I mean by the acceleration? I mean the acceleration of the center of mass. And it's a derivation, which I did in class last time, which is we multiply both of these sides by v, and we get that F times v is equal to d by dt of 1/2 mv squared. So that's just from the linear momentum balance, and this comes from taking the previous equation and multiplying it by v, and then we do just math calculus and we get this result. Now it looks a lot like a thermodynamic statement, but what does the first law of thermodynamics tell us about this system? Well, what is the velocity of this point right here? That's the point that's rolling on the ground, and points that are rolling on the ground, if you look at them carefully, don't have any velocity. That's rolling, not sliding. Anybody got any good rolling things I can use here? I'll return it. You can have it back. Here's this bottle. It's going to roll here. I mark this point that's right on the ground here. And you look at the velocity of that point. Now it's rotating about the center, but if you look at how fast that point is moving when it's on the ground, it's got zero velocity. See, is it going to the right or is it going to the left? Is it going up? Is it going down? Right when it's on the ground, it's not going up or down or to the left or to the right. It's going to the right, my right, your left, relative to the center, but that's not what we're looking at. We're writing the equations of mechanics in the reference frame of the ground. Okay, and that's true for the bottom of a wheel. So the velocity of this point P is zero. So what does the first law of thermodynamics tell us? Well, this point has zero velocity, up or down. This point has zero velocity, up or down. So these two forces here, the normal force in the front, the normal force in the rear, they have no power. So on the left-hand side, we have zero. And then we have zero equals what? d by dt of the total energy of the system. Is the energy of the system changing? No, but you're on the bicycle and you're accelerating. I'm going faster and faster. My energy's increasing, you would say. Wouldn't you? So what's wrong with that statement is that we have 0 is equal to d by dt of 1/2 the total mass times the velocity of the center of mass squared plus other terms. And what are the other terms? We have d by dt of some chemical energy. We have plus d by dt of some thermal energy. And our claim is that the sum of these is 0. But when we say the bicycle's accelerating, what we're doing is we're taking some mixture of chemical energy and thermal energy and turning it into kinetic energy. So when somebody says, quote, bike rider has, say, 1 horsepower, what does that mean? It means there is a 1 horsepower conversion of chemical plus thermal energy to kinetic energy. Now, of course, it's all too tempting to look at this equation and say 1 horsepower is this, so this is equal to that. But this term, as a power term, is 0, actually. Okay, so it's a problem you can get right by the wrong reasoning, but if you do the right reasoning, you get funny results, which is why it's sort of confusing. You can do the homework, but you feel confused. Okay, any questions about this? Now, just so you know what this balance of thermal energy and chemical energy is for a person riding a bicycle, when you ride a bicycle or do any work, going upstairs, jumping, so on, your muscles are where this chemical action happens, and you can measure how much energy people use by looking at the difference between the energy content of their food and their shit. And people do these measurements. They measure the energy content of food. How do they do it? Is they take the food and they burn it, and they look at how much it heats up water. It's called a calorimeter. And they do the same thing with feces, however you want to call them, and they look at the difference, and that's how much energy people use. Then in practice, people know that the energy is converted inside people from bread into crap by oxidation, and so you know that the chemical reactions involve oxygen. Most of the food is about the same as other food. Actually, there are kind of two kinds of food, kind of starch-like foods and fat-like foods. But if you know how much oxygen is used up, you can assume you know how much bread or fat is used up. So they do measurements where they measure how much oxygen is burned by measuring the oxygen content of the air you breathe minus the oxygen content of the air you exhale. The chemical reaction also involves carbon. The carbon content is different for whether you burn fat or whether you burn starch. So in the careful calculations, they look at the carbon dioxide and the oxygen, and they can figure out how much starch you burn and how much fat you burn. And they know that in the long run, is going to be related to the difference between the available energy in your shit and the available energy in the food you ate. And so you do an exercise, you measure this oxygen, they call it VO2, volume of oxygen, O2 because oxygen comes in this molecule with two of them stuck together. And they make these VO2 measurements, looking at how much oxygen is burned. They can figure out how much bread there is. They've done bread experiments. They can figure out, therefore, the energy content of the food you burn to do some exercise, riding a bike. So that means they can figure out what is this term here. The chemical energy. And what they figured out is for animals, most animals, people, most of what they do, the amount that goes from here to here is about 1/4. So if you use 100 watts of chemical energy, you get out 25 of useful work. And that means 75 goes into heat. So when I say it comes from thermal energy and chemical energy, the thermal term is actually a negative term. You actually make heat. So muscles are about 25% efficient. So if a bicycle rider puts out 100 watts, which means they convert something like 400 watts of chemical energy into useful work for accelerating the bike and so on, they're making 300 watts of heat, which is why you get hot when you exercise. Okay. So now I want any questions about this. Yes?
Where do the normal forces on the wheels show up
in the linear momentum balance equation? What I did is because I don't want to, I'm trying to finesse the whole world of vectors in this class and not get all into vector algebra and so on, which is important, but I just don't feel like the 3 lectures on that. So, these are vector equations, and we have to worry about x and y components or whatever components we want. The linear momentum balance equation is a vector equation. It's got a vertical part. The sum of these forces is equal to the vertical acceleration. Bicycle riding on level ground, we know there is no vertical acceleration because it's riding on level ground. Therefore, these two forces have to add up to this one, and they don't show up in this equation at all. Does that answer your question? Okay. Now, in freshman physics, you learn F equals ma. And then you learn m equals I alpha, or torque equals I alpha, which is taken as sort of an analogous equation. But just like F equals ma is a little bit bigger equation than you were used to in freshman physics, it doesn't just apply to particles. It applies to all kinds of complicated systems. If what you mean by F is the total forces, what you mean by mass is the total mass, what you mean by acceleration is the total acceleration, there's a torque equals I alpha equation, which is also big in that sense. It applies to general systems, and it's called, let me just call this 1b, for this lecture I'll call it 3, is this angular momentum equation, angular momentum balance. And we have this cartoon equation for angular momentum balance, which is torque equals I alpha. Just like for linear momentum balance, we had this cartoon equation, F equals ma. It turns out for linear momentum balance, that is the whole right equation, like I just showed you. Total force equals total mass times acceleration center mass. For angular momentum balance, the cartoon equation is wrong. And the general statement of the angular momentum balance equation is more complicated and does not have a simplification like m equals I alpha. But what it says is the sum from all of the external forces or external moments of all of the moments relative to some point, and you have to pick which point, maybe the origin of some coordinate system, is equal to the rate of change of angular momentum relative to that point. In physics classes, they often use the letter L for angular momentum, which is confusing because in mechanics we use L for linear momentum, but that's just the way it is. The physics culture and the mechanics culture haven't resolved that notational difference. So this is called the rate of change of angular momentum. And the general expression for this is a mess. I will show it to you now, not because I want you to remember it or understand it right now, but just so that you remember that I alpha is not correct, is d by dt of the sum added up over all the mass particles of the position of all the mass particles relative to the origin, crossed with the product of each of the mass particles times the velocity of each of the particles. Now, if all you have is one rigid object, which is all you do have in simple physics, high school, physics 112 or 1120, and also often in simple engineering practice, then this term turns into the moment is equal to, and let's just do this in 2D, I, and this is the I, the moment of inertia about the center of mass, times alpha. Alpha is equal to omega dot, which is equal to theta double dot. This thing is the moment of inertia about the center of mass. And this is the moment relative to the center of mass. Total torque. Sometimes torque is called moment. So torque or a moment relative to the center of mass. The world of rotation is much more difficult to understand than the world of translation, except for in that simple case of a single rigid object. Nonetheless, in machine parts, you have to deal with it, but often in machine parts, you can think of the parts as just rotating about one point or one hinge, because that's the way machines are built. And in particular, a special case is a gear. And a gear is a good special case because gears appear all over the place. So if you have a gear, it's something like this. It might have an inner part and an outer part. It might have teeth all over it like this. And it might have teeth all over it like this. And it might be mounted to something. And then we draw a free body diagram of this gear. And when we draw a free body diagram, the hinge is holding it in place. And it's in 3 dimensions, but we don't worry about that. So we don't worry about the force holding it in and out of the plane. We don't worry about the torques in and out of the plane. Then this gear is touching some other gear, which applies a force to it here. And it's touching some other gear, which applies some force to it here. So this gear maybe has an inner radius R1 and some force F1, and it has some outer radius R2 and some force here F2. And then the usual assumption people make about gears is that the kinds of forces they're transmitting are much bigger than what it takes to accelerate the gear. So you think of the gear as massless, or another way to say it as having negligible mass. So if we assume negligible mass, which is the common assumption, and it will give you the right answer, or about the right answer, to most problems in engineering practice for gears. Because as I said, the job of the gear is to transmit forces, not to be in the way, and it's not supposed to be a sluggish thing which is hard to accelerate all by itself. So if we assume negligible mass, we have that the sum of the moments, say relative to some point here, I'll call this point O, relative to O is equal to 0. So even though the gear is moving and accelerating, you do statics with it. So what does that say in terms of this equation here? It says that F1 R1 is equal to F2 R2. So it says that gears are in moment balance, and it tells you a relationship between the forces and the radii of the different points in the gear. And then if you have a gearbox, you have a bunch of these things touching each other. Okay, now let's look at a gearbox. By the way, what does energy tell us about this thing here? What if we just apply the first law of thermodynamics to this gear here? Or basic energy balance, yes? Say again? 0 here? This says the sum of moments with respect to point 0. Yes? What's this O here? That's the name of that point. Like the origin of a coordinate system. Okay, let's assume this gear's got nothing internal going on. It's got no batteries in it. It's got no chemical reactions in it. It's not getting hot. It's not getting cold. It's not burning up. We said it has negligible mass, which means the kinetic energy is 0, which means the power of all the forces acting on this system has to add to 0, because the rate of change of internal energy is 0. So we also have that F1 times V1 plus F2 times V2 has to equal 0 by power balance. Now, is this going to work out right? Well, I'm being very sloppy with the signs here, and that's because I don't want to use careful vector notation, because as I said, I just don't want to get into it. But this point has some velocity. This point has twice as big a velocity. This point is going with the flow here. This point, probably I should draw, let me just change the arrowhead on this one, so that this equation will be correct now. Put the tip of the arrow over here. This one is going with the force is moving with the point of application. This one is going opposite. So any power that's coming in here is going out here. But this point is going slower than this one. So for these to have power balance, these forces have to be in a ratio, which is the ratio of these radii. Because the ratio of the velocities is the ratio of those radii. So if I do this thing again, it gives me, taking into account that the velocities is V1 is omega R1 and V2 is omega R2, again being very sloppy with signs, then we get the power balance equation agrees with the moment equation. Now, the key thing I want to get to today is what happens if you have a gearbox. So when you have a gearbox, you have a box like this, and coming into it you have some shaft which is spinning around and has some torque applied to it. So I'll call this omega 1 and I'll call this M1. Then there's all kinds of gears in here. And you're going to play, starting this afternoon, with a gearbox with all kinds of gears. And comes out a shaft, and there's an omega 2, and there's a torque over here, M2. And what you see is that power is force times velocity, but torque is radius times force, and velocity is radius times angular velocity. So we can re-express that by saying power is torque times angular velocity. So if the gearbox is not dissipative, no dissipation, and not only no dissipation, but no gunpowder and no gasoline, it's a gearbox, not a motor, then we get that omega 1 M1 is equal to omega 2 M2. And again, I'm being sloppy about signs, but what this says is that the power in is equal to the power out. And we can derive this now two different ways. One is by looking at each of the gears one at a time, looking at the forces, look at the moments, assume no friction, leave out inertia, calculate all the forces all the way down the line, and we'll find out that this equation is true. Or we can say that if there is no dissipation, there's no flow of energy anywhere, it must be that the power into the system equals the power out for the gearbox to be constant energy. Now, gearboxes aren't actually perfect this way. They have friction in them. So these equations are all violated a little bit, and the power out is usually a little bit less than the power in. What happens to energy conservation? The gearbox gets hot. Does it get hotter and hotter? No. What happened to energy conservation? There's another energy flow term, which is the heat flow out of the gearbox into the environment. So when you make a machine with a motor, you can think of the gearbox as this thing which approximately conserves energy. Maybe it loses a little bit. Of course, all things conserve energy, but conserves mechanical energy, that the work in is equal to the work out, or maybe you get a little less out. And this is true for bicycle transmissions and car transmissions and little electric motor transmissions and so on. Now, how much do you really lose in a real gearbox it's a property of the gearbox. How good are gearboxes? Does anybody know numbers for these? The very best gears are something like 98 or 99% efficient. And where do you find those is in things like clockworks, where they have very big gears with very teeny teeth. Another place where you see pretty good gears is, say, bicycle transmissions, where the energy loss in the bicycle transmission is a really good one can be, bicycle transmission, I mean the gears and the chain and so on, can be up to like 97% efficient. We measured in my lab one time the whole transmission, including the rolling friction and so on, is about 93% for a brand new Kmart bicycle. Typical cheap gearbox that you buy with an electric motor might be as bad as 50% efficient. It might actually throw away half of the energy. Okay, so that's the basic story. What more you have to learn, I think I'll let you learn about electric motors by yourselves in the lab this afternoon. So let me just take a minute of questions. Did I get you guys to vote yet on anything? Okay. Let's vote. Today's lecture was too fast and or confusing. A. Too slow and or simple or boring. C. Now if it's confusing and boring, you have to decide A or C how to go. And B was about right. Now 85 of you have voted so far, which makes me a little suspicious about the other things going on in this. 89 of you have voted so far. Uh, 51% of you thought it was too confusing. Not a good sign. Okay, so that means you should, let's just take 1 minute for questions and try to cut that down to 50%. One question. Yes? Yeah?
I was thinking if the change in kinetic is positive, then the change in thermal is negative.
Yeah?
The change in chemical.
Are we talking about, say, the bicycle rider?
Yeah.
Okay, so the bicycle rider, the chemical energy is decreasing.
So it'll be negative.
Change in chemical energy would be negative. The change by, say, let's do a real bicycle rider, typical rates, the chemical energy loss is about 400 watts. The thermal energy is positive, 300 watts, and the kinetic energy system, positive, about 100 watts. Does that answer your question? Okay, one thing to do about it is think hard about it. Another thing to do about it is come to office hours. Until yesterday, every single office hours, 1,000 times more people came to office hours than the week before. Literally and exactly. But finally, yesterday, one person showed up at office hours. So.